You should set up like you did for the video, just something nice.
So I think it's, why is the recording stop recording?
Getting to about 9 o'clock San Diego time now, so we'll just introduce ourselves and then we'll start playing the video we've recorded for you. So my name's Dan, I'm a data scientist at nPlan, and
I'm Natalia, and I'm also a data scientist at nPlan.
So we've got a few people from nPlan on the call right now. Carlos, Petra, I think Joao will be joining, and Vahan's in the room here with us today. So a few of the people from nPlan, and yeah, we're a small startup based in the UK that looks at using past construction data to predict or to forecast schedule completion in big construction projects. So we're interested in a lot of aspects of cutting-edge machine learning, and one of those aspects is calibration, which we're going to talk about today. So some, I guess, logistical points. I'm going to be looking at the Zoom chat, and so if people have questions during the video, then if they want to write them in the Zoom chat, they can write them there, and I can try and field them as best as possible. And we're also going to have a Q&A at the end. So if people have things that they'd like to discuss that the video raises, then we can do that live in the Zoom at the end of the tutorial. So one question that's come up on the Zoom already is, are the videos available? Yeah, we have a link. So Natalia's just posting a link to the KDD chat room, and that will take you to the chat, which has a link to the video in it. But we're also going to stream the video on this call. So either way. Okay. Did I miss anything?
Does anyone have any initial questions? Anything from like setting up the notebook or anything like that? Okay, then.
Maybe we should actually point out, yeah, if you go to that link that Natalia's posted, then you can follow the links through. Yes, someone's asking about the code. So the template is at, I believe, was it 2020.nplan.
Yeah, I'm gonna share.
Okay,
so
Natalia's just sharing the code.
If you go to the link I just posted in the Zoom chat, there is a setup for the notebook for the code, and basically if you click this link to take you to the notebook template, you will get to it, and
it will just open in a Colab notebook, and everything should be able to run in the Colab server. So no big setup required. Hopefully that answers your question. Okay, I think we're good to go on the video.
You don't need to make the copy. It's gonna automatically duplicate the existing notebook.
So I think you could save it as an IPython, a Jupyter notebook file if you wanted to.
Yes, you can. You can go to the, basically either in the setup, you can go to the original GitHub page and clone that, or you should be able also to download it from the Colab notebook.
Yeah.
There will be some initial part of the video where we explain a lot of things, so you can set up in the meantime if that's if you need to download it locally or anything like that.
Cool.
So I think we can start now.
I think so.
Okay, can you check? Cool. Okay, I will play the video now, and if you have any questions, leave them in the Zoom chat, and we will either try to answer now or at the end during the discussion.
Hi everyone, welcome to our tutorial where we'll talk about calibration. I am Alan Mosca.
I'm Dan Murphy.
And I'm Natalia Culakova.
Today we'll be talking about calibration methods and measures. At nPlan, we forecast the outcome of construction projects using complex ML models. And one of the things that we started caring about was, instead of having a deterministic output, we wanted to have a probabilistic output of potential outcomes of construction activities.
So if we have a probabilistic output, we need that probabilistic output to represent a true probability distribution in our underlying data set. And quite often with modern neural networks and other classifiers, that's not the case. A distribution that we get out of our classifier may not represent the true probability distribution of our data. And that's what we want to talk about today. Understanding whether that's the case is what we call measuring calibration, and thinking about ways to correct if we have a probability distribution output that's not the same as our underlying true probability distribution. That is a calibration method. So those are the kinds of things we're going to be talking about today. And it's something that we've learned quite a lot about because, as Alan says, because we are looking at probability distributions in our machine learning system, we need them to be accurate. So we've learned quite a lot about calibration, and we wanted to share that in our tutorial today.
So calibration is something that was invented back in the 60s by meteorologists who cared about when forecasting the weather for, say, the next day or a following time period, that if they gave a probability of 80% rain, let's say, for instance, that it would match as close as possible what the true natural probability was at the time. So the simplest way of thinking about it is, of all the times that I predict there is going to be 80% rain, if I aggregate them, it should rain 80% of the time. And this concept has only started coming out in machine learning recently. And we believe it is very powerful because it allows the outputs of modern neural networks to be treated as true forecasts, which can then be input to simulations and can be used to make better decisions.
So what are we going to be talking about today? We will first cover what calibration is in more detail. We will talk about why you should care about calibration and why you should use it in your models. We'll then talk about several different methods for measuring the calibration of your classifier to figure out if and how miscalibrated your model is, followed by a short coding session where we will try some of these methods. We will try to implement them in Python on our test model. In the second part of the tutorial, we will go through a few different methods for calibrating classifiers, mainly focusing on the multiclass classifiers. And we will also try to implement this again in Python with our test model to see if we can improve the calibration of this model. At the end, we will talk a little bit about how you could use the calibration in your real-life scenarios and we will have a discussion about this topic.
We care a lot about calibration at nPlan because we want to treat as much as possible our models as forecasting engines rather than deterministic predictors. And while in research we have seen that there are definitely situations and models that achieve astonishing levels of accuracy, to the point where some benchmark data sets are not really usable anymore as benchmarks, we do not see this happen in real life applications. And this is one of the fun aspects about calibration, is that it helps us understand more about a model's level of confidence and its estimation of both its own epistemic uncertainty, but also the aleatoric uncertainty of the process that it's operating on. And we'll get into that in a little bit more detail later. So if I have a real life data set, and I have my black box ML model, which could be one of many, my accuracy is likely not going to be state of the art. And in the wild, machine learning models are actually part of a bigger system. There could be products depending on them. There would be decisions being made on the basis of the output of a machine learning model. There will be applications that are dependent on this. Could be operating on databases. There could be simulation engines, such as in the case of nPlan. There will be a lot of things, and the ML model is only a part of a much wider system. So sometimes the small percentages matter. So what this means is that when we set thresholds at a high level of sensitivity, we'll care about the slippage of these small levels, especially in applications, as mentioned before, that have a high impact on real life scenarios, such as medical diagnosis. So if we think about the typical neural network, the typical ML classifier that we have now, we should be asking the question, but isn't, based on maximum likelihood estimation, the softmax already supposed to be an estimation of probability? And in reality, the answer is yes, it should be. However, modern models do not appear to behave in the same way. And maximum likelihood estimation is why softmax works. It is only a probability on less complex models and less complex networks. And to understand why, we have to define more of what is a probability. So a probability output is intended to be the true estimation of likelihood of an outcome. So if I take, simplest example, a binary classification task, then I want my probability estimate to reflect the frequency that I would observe in a sample. This means that if I forecast a class to have 20% probability, and I bucket, bin all the forecasts that I've made at the 20% probability level, then I expect to observe that the ground truth is only 20% of the time in that class, whatever the task may be. this relates back to forecasting measures that have been used in the past in meteorology. And modern networks do not actually give probability estimates as their softmax outputs. They do instead give wildly overconfident predictions. So what we see is that the lower probability events are usually predicted with much higher confidence than they should be, even though the error is much lower. So these models are way more accurate on the pure prediction task. In the literature, we see a lot of measures of accuracy, such as F1 scores, precision recall, being used all the time to describe the quality of a model. But these measures themselves incentivize researching for solutions that will be overconfident. One of the techniques that has contributed to the overconfidence of models is batch normalization. And we see this empirically in the literature. So we have a couple of options so to make our outputs probabilistic again. And it would be very easy to just go back to using simpler models, but we do want to instead retain the accuracy gains that have been made. So instead, we have different options such as Platt scaling, matrix vector scaling, temperature scaling that we will see later in the talk. So one thing that can be done is the use of calibration layers. And this is something that we will see later, where I take my very accurate but overconfident model and include a new layer above it that modifies or rescales the outputs of the model so that they look like a probabilistic estimate.
So what actually is calibration? In the simplest terms, it could be described as a measure of model's confidence in its prediction. But what does that really mean? Let's imagine this in a real-life situation where we deploy the model in a medical diagnostic setting in which we are using a binary classification to classify brain scans as ones that show a tumor and those that don't. If our model is overly confident and it doesn't give us probabilities of the answer, but only the straight answer, so it only says this is a tumor, this is not, it might classify one scan as a scan. Don't stare at me like that.
Sorry.
Okay. It's like, am I saying something wrong?
No. I'm just listening to you. I'm thinking.
Okay. Imagine a real-life situation where we have a binary classifier model deployed in a medical diagnostic setting. We are using this model to classify brain scans as ones that show a tumor and ones that don't. Our model is very confident in its abilities, as are we, and it doesn't give us probabilities of the output, but only true-false value for a brain tumor. In this situation, it could easily classify someone who is completely healthy as someone who has a tumor, and we would make medical decisions based on this classification. This could happen very easily if the model encountered something we didn't see in the training data set, and as we know, we can't cover everything. What we would want from the model to do in this situation is show us how confident it is in its prediction, and if it's not very confident, it would leave the better informed decision it would leave it to the doctor to make a better informed decision?
Frequently, people take softmax outputs of their models and try and use them as probabilities. But many recent papers, including one called On the Calibration of Modern Neural Networks that we include in the resources section at the end, have shown that in optimizing for accuracy in recent years, we have sort of left calibration of probabilities behind. A lot of neural networks that use clever tricks to optimize for accuracy actually end up being quite overconfident in their predictions. So taking the softmax output and comparing that to how the true probabilities are distributed, you can see that there's quite a big difference. And this is why calibration is more of an issue now than it has been in the not so distant past. The kinds of architectures and the kinds of techniques that people are using now do force a level of overconfidence, and it's one that we don't tend to measure and that we're not super aware of, I think, on the whole. So that's why we want to discuss and describe some methods today of how to be a bit more aware of when your model is calibrated and when it isn't, and to what extent the problem is. Even if you have a high accuracy, you may have a particularly overconfident model that you can't get accurate probabilities out of. So yeah, I think next we should look at how to view and measure a difference between a perfectly calibrated model and an uncalibrated one.
So next we will talk about some of the measures for some of the measurements for calibration. First, let's talk about reliability diagrams or calibration curves. These are a very insightful and useful visual comparison between true and predicted probabilities. But how do we actually get this graph shown here? What we do is bucket the predicted, bucket the true probability, bucket the predicted probabilities of outputted by our model, and look at the fraction of positives in each of these buckets. From that, we would get a curve similar to what we see in the diagram. If we had a perfectly calibrated model, it would look just like a diagonal line as the red one shown in this plot. But most models will not look like that and will go above or below the diagonal line at different points. By this, we can see at which points the model is overly confident and at which points the model is not very confident. So how can we actually read this diagram? If we had our perfectly calibrated model and the mean predicted value was around 50%, we would have around 50% of positives in this bucket. But the rest of the values that were in this bucket would actually be negative. So what does that mean for the actual calibration curve of our model? For example, if we look at the bucket around 20%, we can see that almost 40% of the values were actually positive. And that shows how underconfident our model was at this point. But on the other hand, when we look at around 40% mark, we can see that in this bucket, only around 30% were actually positive. And the model around this area was being overly confident in its abilities. Most models will exhibit this behavior where there are more confident and less confident at different points or in different classes. That's why this kind of overview and a very detailed measure is quite useful to understand your model. The negative of this approach is that we need to show this diagram. We need to print this diagram for each of our classes. And they are not very practical for a quick look or having it as a part of an automated system, which decides on its own. That's why we have more numerical measures that can help with this.
All of the numerical measures that we want to describe today are actually kind of based around the reliability diagram itself and involve the same buckets and working out the fraction of positives that lie within each of these buckets. But they just gather that information up and aggregate it in a way that allows you to just consume it in one number. So the first measure that we'd like to talk about is one that's quite popular in the literature, and that is one called expected calibration error. And so what we do with this one is we take the absolute distance from a perfectly calibrated model, or our red line in the plot on the slide, and at each bucket we take the distance from this line to our calibration curve. And using this collection of distances, we then take a mean of them, weighting them by the number of points that lie in each of these buckets. So say we had, if we're looking at our plot on the slide again, so we had 10 points in a bucket around 0.2 and 5 points in a bucket around 0.4. We would weight the error at 0.2 higher than the error at 0.4. So yeah, this is quite popular as it allows us to capture the error across the length of the curve and takes into account the number of points within each of the buckets on that curve. Okay, so this next slide is just to highlight the fact that it's one of a number of metrics that you should take into account when you're judging whether your model is doing well or not. So we can see that an increase in accuracy is on the whole accompanied by a decrease in expected calibration error. And we want to get that expected calibration error as low as possible. But there are plots, especially this ImageNet plot on the right at the bottom, where we can see that accuracy is starting to plateau, but we're still getting pretty drastic drastic improvements in calibration error as we continue to train. So the next metric we want to talk about is maximum calibration error, or MCE. And this is pretty similar to expected calibration error. The difference being that when we've got our collection of absolute differences across the buckets in the reliability diagram, we actually look at the maximum difference between a perfectly calibrated model and our reliability diagram. And what that can help us do is try to understand the impact of the worst case scenario over and above the impact across the board. Perhaps we need every probability to be completely accurate. And so we want to get that maximum calibration error right down, rather than on aggregate the probabilities being roughly accurate. And the final metric we like to talk about is root mean squared calibration error. So what this is quite similar to the expected calibration error, but instead of using a L1 distance, we're using an L2 distance. So we're squaring the difference between the perfectly calibrated model and our calibration curve, and then taking a mean of that and squaring and taking a square root. Sorry. So again, we're weighting by the number of examples in each class, and we are then aggregating. So we see one value for the error across the curve, but we also are penalizing large differences over and above smaller aggregation of smaller differences. So again, this serves to move all points towards the perfectly calibrated line, rather than this serves to move all points towards our perfectly calibrated line, and penalizes small deviations a lot less than a single large deviation. It's worth noting, I think, for all of these metrics, the number of buckets that you take is quite important. Obviously, taking very few buckets means that we're going to see quite a small calibration error, as on aggregate, we are going to be correct, right? If you only have 2 buckets, one at a predicted value of 1 and one at predicted value of 0, then we're not going to see a lot in terms of fidelity on our reliability diagram. But if we take too many, then we can't get an accurate fraction of positive values. So there needs to be a sort of balancing act going on here about taking the right number of buckets to get a good fidelity on the reliability diagram, and also being able to see something useful out of, in terms of how calibrated your model is. So with all those metrics, what should we do with them? We've talked about all of the metrics, but in a binary case. And now I just want to briefly touch on what you might do in the multi-class case. So obviously, you'll now have several classes with several different outputs. And depending on your situation, you may want to consider looking at reliability diagrams and metrics in slightly different ways. So consider the argmax of your softmax output. Now, this will tell you if your predicted class is calibrated. And so if that's all you care about, what you're predicting to be the case, then that's a good thing to look at. In this case, you'll just take the softmaxes for all of these argmax cases and plot them on your reliability diagram, as in the binary case. So you end up with one reliability diagram. So yeah, as I say, this is helpful for understanding a prediction system where all you care about is your argmax predicted class. And this, in fact, is what some of the literature uses. There's a paper by Guo et al. Who develop a bit of theory around models that are considered in this manner. Now, where this might not be so useful is if you need to know the calibration of all the classes of your classifier, whether it is the argmax case or any of the other softmax outputs. And that's the case for us here at nPlan. We need to know whether all of our classes are calibrated, and that's because we use the classes as a probability distribution from which we can sample. So yeah, we need to know that they're all calibrated. And there are several ways you might be able to combine the binary calibration methods to understand the multi-class calibration for this kind of problem. One way might be to display each of the classes separately, and so look at reliability diagrams for each class considered in a binary manner, in a one versus all manner. And this might be good if you really want to know to what level each class is calibrated or uncalibrated, and it helps you get quite a lot of detail. But with something like Cypher 100 or ImageNet, where you've got hundreds or even thousands of classes, going through each reliability diagram becomes quite difficult, and you're not getting the information that you might want. So what you can do is aggregate all of your softmax outputs together. And if you do that, you can then plot that all on a single reliability diagram. So you're seeing results for all of your negative cases and all of your positive cases at the same time. So I'll run through a bit of code in a minute that will help us understand these few different ways of viewing reliability diagrams. But I just wanted to say first that it's not set in stone which way you should view these reliability diagrams or metrics for your multi-class models. You really need to think about what you care about. Do you care about calibration of positive class only, or do you care about calibration across the board? Would you like to be able to look into each class in detail, or do you just care about aggregation? So that's reliability diagrams. The other aspect of aggregating is also aggregating the metrics that we've just described. So these metrics, we can either take a mean of them across our one versus all classes, or we can weight this mean by the number of positive cases that we see in each class. So maybe we've got one class that is very heavily weighted, and we care about the calibration of that class a lot. So perhaps we want to weight calibration error heavily on the calibration of that class, and then we can see an improvement that's weighted on the calibration of that class. Or perhaps if we're looking at our reliability diagram in aggregate, we don't need to do this kind of averaging. The averaging is taken care of by the aggregation at the reliability diagram stage rather than at the class stage. So yeah, you have a few options here of how to aggregate your information, and each of these options has its pros and cons. You need to think about your case and how these different options might fit in there.
So in this coding session, we will focus on some of the ways you can measure calibration of your model. We will be working with a test model from Keras. So we will not be training our own model just because of the time constraints. So we are using the Cypher10 image dataset, which is a dataset of very low resolution images that is often used for testing different models, as they can work faster with this. We already prepared this template where we have some of the libraries. We have all of the libraries we will need. So we have NumPy for all the numerical calculations. We have TensorFlow and Keras for our model and our dataset. PyPlot for plotting some of the plotting the reliability diagrams we talked about. These diagrams we will get from scikit-learn calibration curve, which is a great method for just getting all the values out of your model. And we will also use some of the scikit-learn metrics to see how accurate our model is. So we here you can see. So we need to run all. So we need to run these cells one after the other. So you would. First, we import all of the libraries, and then we will split the dataset into train, test, and validation. Like we mentioned in the presentation, we need to measure and calibrate our models on the validation set. So we need this three-way split. This will take a few seconds, and then we can look at how does this data look like. So you can see one of the images right here. It's a car, but it's very low resolution, so our model can work with it fast. As the next part, we have some small ways of pre-processing the data. So we normalize the data, we translate it to categorical values instead of continuous as they would be originally. if you are interested in the model we will be using the Keras ResNet model, which is already trained on these 10 classes. And we also have a binary simplified binary model that just tries to decide between classifying dogs and cats. As the next step, normally you would actually prepare your model and train it, but because we already are using a trained model, we will just download and load the model we will be using. After that, we will split the data into data prepared for the binary model that decides between cats and dogs. So we will need to just take out the classes 3 and 5 and label them as 1 or 0. So if we try to predict on the test set for the binary and multiclass model, just to look at what the accuracy and validation loss are for the model we are using, we can see that the accuracy is fairly high, but we don't know anything about how calibrated the model is or how confident it's in its predictions. Due to that, we will now follow up with the measurement with the metrics for validation. First, we will try them on the binary model we have, using the calibration curve to plot our predicted values against the true probabilities. So, as we mentioned before, you can look into the documentation for the scikit-learn calibration curve, which will basically do all the preparation for us. This method. Should I just write the code? Okay. So the calibration curve, as suggested here, we can pass the y values, the true y values, and the probabilities predicted by our model. We will pass this for the binary model as a first step. Then you can also pass, if you want to normalize the values, what strategy you want to use, and how many bins you want to split the predicted probabilities into. We will be using 10 bins today, but it will depend on your model. What this method returns is, as mentioned in the description, are two arrays, true probabilities. Yes. Okay. What this function returns, as mentioned in the description, are true and predicted probabilities. So we will expect these two values to come out. We can try displaying one of these arrays just to see how it looks and just to get a feel of what we should expect. So it will be an array of 10 values, and we can see that these are going a little bit up and down. They are not really monotonously going up as we would expect from the very well calibrated model. So how can we nicely display this? We will be using the matplotlib pyplot library to display this curve. So just copying here from our template, we will create this function that plots a reliability diagram for us. what we need in this function is to pass the true and predicted probabilities that were returned by the calibration curve. And if we want to have a label on the calibration curve, we should also specify it as a string value. We want to plot it as a, we're going to use the normal matplotlib pyplot options to just plot a figure. You can specify the figure size if you want, but it's not necessary. So what we want to plot is one diagonal line for the perfectly calibrated model. So I'll just copy that from our ready solution. This is just to compare how our model is doing. And then we want to plot our line as the function of the predicted probabilities and the true probabilities. You can specify the label. We will be using the model name, and you can obviously specify some formatting options if you want. But this again is not necessary. So we will just put here some labels for the axes and the ticks, and which will take care of some of the formatting for us. But just for a quick look, you wouldn't really need that. If we want to print this plot, we will just call the function with the returns of our calibration curve function. So we pass the true probabilities and the predicted probabilities. And we can pass the name of the model, which is our ResNet model binary. So if we run this cell, we should get our calibration curve. So we can see that it's not really a curve, and it's clearly not very well calibrated. It is very underconfident at certain points, and overly confident in others. So we will try to improve this later on by actually calibrating the model. So thinking back to the numerical metrics, we have three options which are fairly similar. So as one of the numerical metrics, we will try to implement the maximum calibration error, as we can see that some of these points in the reliability diagram are quite high, and we would like to optimize this. So for the function for maximum calibration error, we are not concerned by the number of points in each bucket. So we only need the true and predicted probabilities that were returned by the calibration curve function. From this, we are trying to find the maximum distance between all of these values. For that, we will iterate over all of the buckets. So we will iterate over the predicted values, and we will try to get the maximum value between our existing maximum calibration error and the new distance, absolute distance between the true and predicted probabilities at this point. So our starting, as we are using absolute distance, our starting value will be 0, as none of these should go lower. And at the end, we will return the overall maximum calibration error. We have to pass the binary values for our true and predicted probabilities. And now if we run this, we should get the maximum calibration error for this class. We will iterate over the length of these, not over the actual values. And now we actually get the maximum distance. So this, in the ideal scenario, this value would be 0 for our perfectly calibrated curve, but we can see it's 0.5. So we can only assume that's the distance here at around 35%, where we can see a huge spike. So how would we extend one of these or any of these to a multi-class problem? For the reliability diagram or the calibration curve, we would treat this as a one versus all problem. So for each class, we would mark this class as true and all the rest of the classes would be false. And we would plot a similar diagram for each of the classes. This would give us lots of insight for each class, and then we could go with a more summary metric, like the expected or maximum calibration error. So let's go with that. Let's try to implement one of the other ones now. Let's try and go with the root mean square calibration error for a multi-class model. So that's how we can get the maximum calibration error for a binary classifier. We can see that ours is quite high, as the ideal would be 0. But we can assume that because of this high point right here, where the difference between the perfect calibration and our calibration line is quite big. Just to not waste our time with implementing the rest, I'll just copy them over, but you could implement them yourself and you can find them in the completed tutorial we have on the website. So just copy over the expected calibration error, which is the average, weighted average of the distances. Hopefully this runs, and we can see that the expected calibration error for this binary classifier is fairly low. We would assume that the number of values in these higher spikes is probably quite low, and that's what's driving that. For the root mean square error, we will do the same thing. Just copy it over. Again, you can find all of this in the completed tutorial. And here we can see again that it's a bit lower, quite a bit lower than our maximum calibration error. So we can assume that those points that have very high difference are fairly, have very few examples in them. So for that, we can move on to measuring the calibration in multi-class problems. We have 10 classes, so if we were to look at the reliability diagrams, which we will do as a part of the exercise, we will just iterate over all of the classes we have and run this function to plot the reliability diagram for each of them. So we just pass the results of the calibration curve function, and we can see the reliability diagram for each of our classes. So we will now implement the RMSE, or the root mean squared error, for the multi-class model. What this does is just calculate the weighted root mean squared error across all classes. So what we need to do is iterate over all of the classes using the length of the shape of the Y through array. This way we will iterate over every class. We can just use the calibration curve function from scikit-learn to get our true and predicted probabilities values, and this function will do all of that for us. So we will now get this for each of the classes, and then we will average all of that in the end. So we will pass the Y true for our class, and also the Y predicted for the same class, and specify the number of bins as 10 again. You can play around with different bin sizes for this model or for models you are working with. This is quite an important parameter here. For root mean squared error, we also need to know how many elements are in each of the buckets in this class. For that, we will use the numpy histogram function, which will split our space into a specified number of buckets, and also tell us how many values there are in each of these buckets. As first, we pass array of the values we want to split, which is the A class. Oh, should this be again that? Or should it be?
Yeah. Oh no, it shouldn't be, because. Oh yeah, go for it.
Yes. Okay. So we will again pass the Y predicted for the class we are working with. We will specify the range we want to split which is 0 to 1, and we will specify the number of bins, which should be 10, but we can also use the length of the probabilities. This will be an array with two elements. First of them is the one we want, which is the number of elements in each bin or bucket, and the second one will be the boundaries of each bucket, but we don't really care about that right now. We want to calculate this RMSE for each of the individual classes and save them in a good way. So we will create a list for them and then just append to this list. We can just use the function that we created or copied before that calculates the binary RMSE, where we can pass the true and predicted probabilities returned by the calibration curve function and the bin sizes. This will calculate the RMSE across all of our buckets, and it does that by summing all of the squared distances between our perfect calibration curve and the calibration curve our class has. So just copying this over to use the same function, we'll just return, we just append the results. So we pass the true and predicted probabilities and the bin sizes we got from the histogram function. After this iterates over all of our classes, we can return either the mean across all of these values, or we could return or we could return the weighted average over these classes. So we can do both by just using the NumPy mean function and then calculating the weighted average. Where did you get this class with? Sorry.
They're not defined.
Okay.
I just said you could do this.
Okay. Or so we can return the mean of across all of these RMSE bins, or across all of these RMSE values for each class. So that would be just using the NumPy mean function. Or you could also calculate the weighted average, which you would use, which you would weight by the number of elements in each class divided by the number of classes we have. This is not really necessary for this purpose, as every class has the same number of elements in them, as the dataset is structured that way. But if you had a dataset that would have very big differences between the classes, this might be a good idea. So now let's just go and call the RMSE calculation multiclass with our true and predicted values that we specified above. So just going back to where we split our dataset, our true values are evaluated on the validation set. So we will use the y-val, and we will use the y-pred for the predicted values. So just passing the true and the predicted values and trying to run this. Let's see if we get an error. We do, because we made a mistake while naming these. It should be bin sizes. And now when we run it, we get our overall RMSE across all classes, which is 0.027. If we want to also see the calibration curves for each of these classes, we can just call our function that we defined above for each of these. So we'll just call the plot the reliability diagram with the probabilities true and predicted returned by the calibration curve function for each of these classes. We don't have to specify model name, or we could just say that this is the class and say the A class. Let's see if we can get all of the different calibration curves. So if we scroll through this, we can see that each class has quite a variety of shapes. And as such, we will try to improve all of them. With some of the calibration methods, they target each class with different parameters. Some of them, on the other hand, use one parameter to try to improve all of them across board. So this is the part about measuring calibration. If you want to see how to implement the expected calibration error or the maximum calibration error for all of the for the multi-class model, you can try it yourself, or you can use the examples we show in our completed template.
Frequently, each of those buckets contained true and false examples of his classification. And using that data, he saw that it fell into a sigmoid shape, which is what we'd hope for something that can be classified with a support vector machine. You know, you see quite a few examples around the boundary, and then as you get further away, as you get further away, you start to see become a lot more confident in your classification. So I'll just display, I'll just display this image of maximum margin classifier to sort of try and explain that. So perhaps this is the red line is the plane that you've selected for your support vector machine, and the logits are the distance from that plane, right? So we can see that a lot of points are clustered near the plane, and then as you get further away, the points spread out. And so you can see applying a softmax to this will help you to get a classified solution, but it may not tell you about the probability that your classification is correct. He put a couple of parameters inside the logistic function, and that helped to move and scale the function to fit his data. And so he was able to obtain proper probability estimates using these SVM outputs. Now, that was unusual at the time. People were used to using SVMs purely for classification purposes, not to retrieve actual probability estimates from them. The second paper that I thought might be useful to talk about is a paper by two people from Cornell about obtaining calibrated probability estimates from several different network types using several different scaling and other non-parametric methods. So this paper is written a lot more recently than the Platt paper, and looks at using Platt's method on SVMs, but also on neural networks and other classifiers. And it assesses the calibration using the methods that we've described earlier in the presentation, talking about plotting reliability diagrams and then assessing the ECE of these models. And then it goes a step further, as I say, to try and fit a sigmoid to our post softmax or post SVM output, and fits a softmax to these logits, and then sees what the scaling does. And at that time, it was concluded that using this kind of scaling for neural networks wasn't really necessary. The shapes that these two researchers saw weren't in keeping with plotting a sigmoid, and so they concluded that neural networks at that time were fairly well calibrated already without the need for extra scaling. They agreed for the use of scaling in the case of SVMs and in the case of some other model architectures, but the conclusion that they came to was that any method that they tried to calibrate neural network outputs got them negligible results. So that was the state of affairs in 2005. And we'll jump forward quite a few years to a paper called On Calibration of Modern Neural Networks. And this is where a lot of the content for our discussion today has come from. And so this is a paper by Guo et al. And this talks about how more complicated modern neural networks with changes in the way that we've done training and changes in the way that we've been able to put in a lot more layers and a lot more nodes into our networks has actually led to them becoming quite overconfident, and how that needs to be addressed. Or at least needs to be made, people need to be made aware, and we need to make sure we keep an eye and think about how we can solve this problem making sure that our networks aren't overconfident. If we're naively taking softmax outputs as posterior probabilities, then, well, we've talked about how that might become a problem. So it's certainly something we need to keep an eye on. And so the first thing I want to draw your eye to in this slide is this plot on the left. And so on the left-hand side of this plot, we can see the reliability diagram at the bottom for a LENET or LENET from 1998. And this is classifying CFAR 100 data. And we can see that its accuracy is quite low, but its average confidence is also quite low. And this translates to actually quite a calibrated model. So we haven't been able to maximize accuracy because of the simplicity of this model and the simplicity of the way it's been trained. But we have, in fact, retrieved a quite calibrated output. And so we can see, because these bars are all sitting quite close to this diagonal line, we actually see in places it is underconfident in its predictions, especially when it's outputting a high softmax. So that was the case in 1998. And then if we look on the right-hand side of this diagram, we see the case in 2016 with this ResNet here. So it's a lot more complicated. The ResNet they've chosen to use in this paper is 101 layers. And so you can imagine the complexity is quite high. We've also introduced quite a lot of training tricks. So weight decay, batch normalization, these are all things that have come in the interim. And we can see that we've been able to push the accuracy up by quite a way. We've come from just over 0.5% accuracy, 0.5 accuracy up to around 0.7. But our confidence has jumped as well. And that translates to quite a uncalibrated, overconfident model, which can be seen by the reliability diagram in the bottom right-hand corner. We can see that our blue bars are sitting well below the diagonal line for a perfectly calibrated model. And so, yeah, we've managed to push this accuracy up, but we've ended up costing ourselves in terms of being overconfident with our posterior probabilities. So the question is, can we work out a way, or can we use one of the methods that they suggest in this paper to actually correct this? So the second thing that I'd like to actually draw your eye to here as well is this plot down at the bottom. So what this plot describes actually is how, by increasing certain complexity metrics about the network and using certain training tricks, we've actually cost ourselves in terms of ECE. So if we look at this first plot on the left, we're increasing depth as we move to the right-hand side of the diagram. And we can see that the error is steadily dropping, as we hope. But the hidden thing that people haven't been as aware of is that our ECE is creeping up, or at least moving up in the early portion of the diagram. So yeah, an added section of ECE of 0.1 is problematic. And we can see a similar story when we vary width. So yeah, we're seeing a drop in error, but we're also seeing a increase in ECE that for a lot of people, I think, has gone quite unnoticed. This trend is also true with batch normalization. We can see we're dropping error, but we're also increasing ECE, and also true with some measures of weight decay as well. So all of these changes and advances in network architecture that allow us to get better accuracy have actually cost us in terms of calibration. That's the thrust of this paper. And so they go on to say, well, how can we fix it? Here are some methods, and they talk about both the binary case and the multidimensional case. And so for the rest of this presentation, I think we want to talk about some of the methods they present and how you might implement them in a machine learning pipeline especially using Keras. That's the code that we have at the moment, and show you that you can, in fact, see overconfidence in your predictions, and that you can also see a correction in that overconfidence using some of the methods they present.
Now that we can measure how calibrated our model is, in the second part of this tutorial, we can dive into some methods for improving the calibration if the model is miscalibrated. So we can achieve results that are more close to true probability distribution. There are quite a few different methods for calibrating binary classifiers. We will focus mainly on isotonic regression and plot scaling, and we will then cover more methods for we will then cover some methods for calibrating multiclass classifiers that are extensions of plot scaling. We will talk about temperature scaling and matrix and vector scaling. All of these methods are applied on a validation set and are evaluated on the test set. If we didn't use a validation set, we would get overly optimistic calibration results, and that wouldn't be what we really want to achieve. So how can we actually improve the calibration of our model? We know that in the past, simpler models were better calibrated, but if we want to use those again, we would use all the achievements of better accuracy and other advantages of the new, bigger models. So how can we try to keep the accuracy as close as possible to our current models, but at the same time improve the calibration? Thankfully, there are some calibration methods that allow us to do exactly that. These are all of the methods we will be talking about today are used after training, so you don't have to train a new model or retrain the model you have just to improve calibration. As we mentioned, they all require you to have a validation set, and the assumption you need to keep in mind is quite obvious, but it's good to remember this. All of the train, test, and validation sets are drawn from the same distribution. All of these methods are fairly simple to implement, and as such are very easy to add on top of our existing models.
The first method that we want to talk about is isotonic regression. So yeah, as Natalia said, we'll go through a couple of binary classification calibration methods first. And then from there, we'll expand one of those methods to talk about multiclass calibration as well. So the first method we want to talk about is isotonic regression. And this is a non-parametric method for calibrating binary classifiers. So what we want to do, if you had a reliability diagram in front of you and you wanted to know how to translate your predicted probability into a true probability, you might fit a piecewise function, a piecewise constant function, that minimizes some loss to that reliability diagram. And that function will then provide us a translation between our predicted probability and our true probability, right? So there are a few algorithms out there to implement this kind of a method, and it's minimizing this loss function. And yeah, we would then use this translation function, f here in the formula, as the last step in our neural network. We take our output and then run it through this f function to provide a true probability estimate. Okay, we got something similar with Platt scaling. So this time, instead of scaling our output, we take one step back and scale the logit, the final output of the dense layers before a sigmoid activation in a logistic regression model, in a binary classification model. So without calibration, we'd have this formula on top here, where we're taking the sigmoid of this Zi logit to get our probability estimate. And with calibration, we're trying to find two parameters, A and B, where transforming them in such a way before they are put through the sigmoid gives us a better estimate of our probability. So yeah, the main idea with both these methods is we're taking some aspect of our trained neural network, whether it be our output probabilities or our logits before the final layer. We're taking something and we're trying to scale it or find a translation function somehow that allows us to map to the true probabilities.
Next, we will be talking about some of the extensions for Platt scaling that can be used for a multi-class model. First one is called temperature scaling. It's probably the simplest method of calibrating because you only train one parameter t, also called temperature, for all classes. This method doesn't change the maximum of the softmax at all, and as such, it keeps the prediction class and accuracy of our model, which sounds perfect.
It's called temperature because with higher values of t, we'll see a greater spread across our softmax output, and with lower values of t, we'll see it concentrate towards the maximum value. And so it's kind of similar to simulated annealing or other methods that use a temperature parameter, right? Where a larger temperature parameter induces more entropy and a smaller temperature parameter reduces the entropy.
Last method or two are called matrix and vector scaling. As mentioned before, these are again just the extensions of Platt scaling. So they again, no, doesn't matter. So what is matrix scaling? It is basically just a linear transformation that's applied to the two parameters which we are trying to optimize. These parameters are the matrix W and the vector B, and we are trying to optimize the values of these two. This can be, if we have more classes we have, the size of the matrix grows quadratically, which can be very impractical for a lot of classes. For that purpose, vector scaling was invented, where you restrict the parameters of the matrix W to only the diagonal axis. And as such, your calculations are much easier, much simpler.
The smaller number of parameters in vector scaling helps to avoid calibration overfitting as well. So we want to sort of balance the flexibility that a lot of parameters like method like vector scaling has, matrix scaling has. Sorry. We want to balance the flexibility that using a lot of parameters like a method like matrix scaling does with the possibility that we might overfit. And so shrinking the parameter space by only using parameters on the diagonal of the matrix allows you to do this.
So now we can again switch to our notebooks and we will try implementing few of these methods and see how they improve the calibration of our test model.
We've talked about several different methods of calibrating your classifier. Now let's have a quick look at how you might implement those. So first, as with the metrics, we're going to take a look at the binary case. And we'll go through a couple of binary cases, and then following that, we'll expand to the multiclass case again. Okay, so in general, we're looking at our model and we're trying to find some output of the model, be it the softmax output or one of the logic outputs, an intermediate output, and we're trying to find a function that helps us translate that into a calibrated probability. And we'll judge whether it's calibrated based on our reliability diagrams. And to be honest, most of the time, or some of the time, the reliability diagrams help us find what that function might be. So the first method I want to talk about is isotonic regression. Now, this is a non-parametric method. And what that suggests that you do is, as we described earlier, fit a stepwise regression function to one of these outputs of your model versus a probability output, and use that to sort of translate and scale your output to get a calibrated one. So what I'm going to do is put my answer into the little cell in the notebook here, and I'll just walk you through it. So what we're going to do is we're going to import the isotonic regression function from scikit-learn, and we're going to fit that to the bucketed values in our reliability diagram. So this is equivalent to fitting it to our softmax output. So we are, let's see, so we're fitting a function basically to this monotonically increasing function to this plot here. And following that, so we've got our function. And then following that, I'm going to plot it again and plot the function against our reliability diagram. And then after that, what we want to do is use the model to predict to get our softmaxes, and then use our regression function to transform our softmaxes into calibrated predictions. And so using these new calibrated predictions, I'm going to plot a new calibration curve, and we can see how that looks with a new reliability diagram. So that's what that cell is going to be doing. And we can see in this first reliability diagram plot here, we have fitted our isotonic function, and it fits okay. Obviously, there are some problems here with the peaks and troughs of our reliability diagram. So the isotonic function hasn't been able to capture everything completely, but we are seeing it tracing some aspects of our curve there. And now this is the reliability diagram that we see following calibration by isotonic regression on the softmax outputs. And we can see, yeah, it leaves a bit to be desired. However, this may have been a result of our choice of what part of the model to use isotonic regression on. If we'd used it on, say, the logits, the step before our logistic function, as in Platt's scaling paper, perhaps we would have seen a better relationship come out at the end here. And so speaking of, let's actually step forward and talk about Platt scaling. Okay, so we recall that Platt scaling, we're fitting a softmax, we're fitting a logistic function, a sigmoid function, to the logits of our classifier. And so I'm going to paste some code in again and walk you through it. So what we're seeking to do here is to find the optimal scaling values, A and B, that scale our logits before we feed them through a logistic function, so that they fit our reliability diagram in logit space really well. And this is exactly what Platt was trying to do. So the way I've gone about this is, we know that the final node of our binary model is a sigmoid activation node. So I step back through that node using the logit function from SciPy. And so we get all the activations of our second to last layer in our network. And then what I've done is written this little function that takes A and B in as a tuple of arguments and computes the negative log likelihood. So this is just a binary cross entropy or binary negative log likelihood that we care about for this network, but scaled using A and B, right? So we are getting A and B out of the tuple, we're scaling our logits by A and shifting them by B, then feeding them through the sigmoid function, and then calculating our negative log loss. And this process should give us out the underlying true probability distribution. Now, this is a result that obviously we're not going to prove in this session, but it's a well-cited result. So optimizing this function ought to give you out a true probability distribution. And so we are going to use SciPy optimize minimize to optimize this function with respect to the two arguments in X. And I've just chosen Nelda-Mead for speed. No need to calculate gradients, of course. We're just stepping over a 2D space rather than a very complicated space like one that you might find in a full network. So we only need a simple optimization method. And so I'm going to click run on that. And it'll take a little while to predict, and there we go, it's predicted. Right, so we see that our optimization it's converged in 87 iterations, and we've got two X values here. So this is going to be our A, and this is going to be our B. And so why don't we, if we get our model and we predict using this scaling. So what I've done here is we're getting our predictions and we're getting the logits from those predictions. We are scaling them according to the Platt rule, and then I'm going to calculate our new calibration curve and plot it next to our old one. Okay. So you can see here, this is the test data now, not the validation data. We've calculated our parameters based on the validation data, if you see here. And we are now predicting on our test data. So uncalibrated, our model looks like this, which obviously is not very good. There are portions where it's overconfident, portions where it's underconfident. And then we have run our calibration scaling to get these corrected values. And this gives us this second reliability diagram, which obviously is a lot better. Now, to just drive this home, why don't we calculate one of our metrics? So let me fetch the name. Let's look at ECE. So if I copy this down, in fact, I'll copy this down. In fact, I will copy both of these down. Okay, so we care about the test case. So we're going to look at y test pred binary and calculate up here. We've got the prob true binary and prob pred binary, so we'll copy them in as well. In fact, we've got them down there already. And then we'll get another one of these for the corrected version. Sorry. I think, let me check the name there. Y test protocol. Okay. Sorry. So it's Y test pred corrected. So we're calculating the bins, and then we're calculating the ECE in each case. And we can see that the ECE has stepped down from 0.15 all the way down to 0.02. So the model is both visibly a lot more calibrated, and also when we check the metrics, it's a lot more calibrated too. So both of those methods help us to understand that we've made a good choice with Platt scaling in this case. So that's implementing calibration methods for binary models. How might we do things for multi-class models? So we're going to think again about our Cypher-10 large model. So I've actually got a second notebook here that I'm just going to load up. And I'll run a couple of these cells so we can get the model loaded in and the data manipulated as we did before. And then we can have a think about the reliability diagrams in a multi-class case. So as Natalia said earlier, you may think about using reliability diagrams for each of the classes to understand how each of them is calibrated, but perhaps what we care about as well is how the model as a whole is calibrated. Is it on the whole overconfident or underconfident? And so one way of doing this might be to flatten your entire test set. And that's so take your list of vectors of softmax outputs and put them all next to each other, append them to one another. That's what the flatten method does to this array. And then we're going to feed that whole set of softmax outputs and predictions. A whole set of one hot vector targets plus our set of flattened predictions into the calibration curve. And so this is, I guess, akin to plotting all of our softmax outputs on the same calibration curve. And we can see what comes out. So we're predicting on the test set, and we're looking at what comes out. And the reason that we're predicting on the test set, of course, is so that we can understand how uncalibrated that is, so that when we calibrate, we can see the change. Right, so we see here there are systematic portions where it's under and overconfident. At high softmax outputs, it's quite overconfident, and that's indicated by this sort of low below the line value here. So yeah, for instance, when we're outputting around 0.8 for softmax, actually we're only getting 0.6 of our instances in that bucket being positive. And similarly down here, we're getting systematic underconfidence. So obviously there's a problem with the way this model is working. And we want to think about how we might fix that. So here I'm going to show you how to do temperature scaling as we described in the presentation. Obviously, you can use this method, and I'll point out when you can change it so that we can do the other methods we described, matrix and vector scaling. So what I want to do is make a copy of my model. And then somehow I want to get to the logits, right? So what I'm actually going to do is make this new model output the logits of my network. So one step before the softmax. And so to get to that, I'm just going to reach into some of the Keras code using the list of layers inside this model. I want to get the second to last layers output, and then feed it through a dense layer with the same weights as the final layer of our previous model, but this time without a softmax activation. So if you take a look inside the weights of our old model, you can see that the last layer is a dense layer with 10 units output size and softmax activation, and we're going to change that to no activation. And then we're going to build a new model with those outputs and then set the weights of our new final layer to match the weights of our previous final layer. So I'll run that. Great. And then I will compile it. Obviously, we're not going to train it, but you need to compile it to get predictions out. And we'll get those predictions out. And so similarly to in the binary case, we've got this function that we want to optimize with respect to some list of arguments. And this time, we're only going to be using a single parameter. We use that temperature parameter. And we want to divide our logits by the temperature parameter and then feed them through the softmax function. So it's a very similar idea to what we were doing in the binary case, just a slightly different function that you want to optimize. And then again here, I'm just using the SciPy, this scikit-learn, implementation of log loss to calculate the log loss, and then we're trying to optimize that with respect to t. So run that again, and similarly, I'm going to use another mead. We're only stepping through 1D space this time, not 2D, so we don't need any heavy machinery. You see it's converged in 50 iterations this time. And so, spoilers down there. So we know that we've got something out and we know it's converged. And yes, it's worth pointing out again that what we're doing actually is optimizing these with respect to the validation set, not the test set. So now we need to evaluate how we've done based on the output from the test set. Right, so I've made the predictions on the test set and then got our scaling parameter out and scaled, fed through the softmax function. And now I'm calculating a new, so I've got my corrected predictions and I'm calculating a new calibration curve based on those corrected predictions. So yeah, we can see down here that our reliability diagram is again orders of magnitude better calibrated than our previous one. So this is a test set before calibration, and this is a test set after calibration. And remember that we use the validation set to calibrate rather than the test set. So this is sort of reinforcing how good how well we're doing. And just to round this whole portion off, actually, yeah, to remind you, we've done, in this case, we've looked only at our aggregated reliability diagram. This will work in any of the cases that you choose to aggregate your calibration results. In fact, this is the only way to do the calibration. The aggregation is just a different view into how that calibration has worked. So perhaps in this case, we'd be plotting 10 calibration curves and seeing them all improve. But our actual method of using this function and optimizing log loss over the whole model, that doesn't change. That's the only way that you can do things. Sometimes you might need to use a more complicated or slightly more powerful optimizer. So in the case of matrix and vector scaling, we change our parameters here. So our parameter t would no longer be a single scalar value. It would be either a matrix or a vector. And we would have, so we'd have a multiplication here and by a matrix and some vector as well that we add on. This would be matrix and vector scaling. And obviously in this case, we would want the parameters that we are optimizing over to be these matrix and vector values. And the formulation of this function wouldn't look quite like this. What we'd actually want to do is flatten, well, stack all of our matrix and vector values into a list that, so the function that we're optimizing over would be, the structure of them would be invisible to this function. And then we'll hand all of those parameters in and construct them into a matrix and vector at this stage. But the method itself doesn't change. What we want to do is just use some optimization function to optimize over that. Okay, and just to, as I say, to round things out, what I want to do is look at one of the metric calculations for this example that we've just been through and look at how that improves over the course of this calibration. So what I'm doing here is just looking at the calibrated version and the uncalibrated version of the RMSCE. And we're looking for a decrease. So I'll run it again with our new values. And we can see that we've gone from 0.02 all the way down to 0.004. So we've seen a pretty good improvement in the RMSE there. And obviously just from eyeballing the plot here, we can tell that we would get an improvement in all of our metrics. So yeah, that's temperature scaling, and I hope you can see how you'd implement matrix and vector scaling from that example as well.
Thank you so much for sticking with us through this tutorial. We have introduced calibration, which is a concept that is becoming more and more relevant in machine learning. And we have explained why it's important, why do we particularly care, but also why is it important to have probabilistic forecasts as outputs of machine learning models rather than the deterministic predictions. And we have explained what the literature that is available is.
We have covered several methods of measuring calibration. We have talked about reliability diagrams and also some numerical metrics. Specifically, we talked about expected calibration error, maximum calibration error, and the root mean squared error. These were all very similar, but they focus on different downfalls of the models. We also covered a few different methods of calibrating the classifiers. We talked about two methods for calibrating binary classifiers, isodonic regression and plot scaling. And then we talked about few different methods for calibrating multiclass classifiers, which are all extensions of the plot scaling, specifically temperature scaling and matrix and vector scaling. In the literature, you can find more ways of calibrating that could maybe fit your purpose better. We also showed some examples of how you can implement these metrics and methods for calibrating, and we have shown how they can work well, but also how sometimes they don't work as well as we would like them to.
So those concrete examples will be available to you after this tutorial. We're going to make both the empty template and a template with model answers available, so you can look at how we've implemented temperature and matrix and vector scaling layers in Keras, and how in the binary case you don't even need to dip into Keras. You can use other optimization methods like ones available in SciPy. We've also been able to show you a slightly larger and more complicated model that really displays how for modern, large, deep neural networks that are trained to very high accuracies, like the large model that we showed you, we can see actually, along with very high accuracy, we are getting overconfidence. And this is exactly the problem that we're trying to solve with these kinds of post hoc calibration methods.
Thank you, everyone. And now we would like to hear your questions and comments.
Okay. Great. So thanks for sticking with us, and we hope you found that interesting. Yeah, one question that I think we haven't, so yeah, I've been answering a few questions in the chat, and hopefully I've answered them to people's satisfaction. One question that we got from Wenting was, I'm curious in which case we need to do model calibration. So does it depend on model complexity or data imbalance? I say it doesn't really depend on those things that you mentioned. It's more about what you want to do with the model. So if you need your model output to reflect a true probability distribution, that's when you should do calibration. So in our case, we're looking to get a probability distribution from our classifier so that we can then sample accurately from that probability distribution, and that feeds then into a Monte Carlo sampling pipeline, basically. And so we need our outputs to accurately reflect the underlying probability distribution. That's why we care about calibration. And so, yeah, the another example is the example Natalia mentioned at the start, which is like a medical diagnosis example. And actually, I think someone in the chat posted a paper. I think it was Saran posted a paper about diagnosis of skin issues using images. And in that case, you might care, how confident is your classifier about classifying the image into one of many classes,
Yeah, so I guess one thing is that you might want to measure calibration in lots of these cases, but maybe in some of them you don't really care about calibrating your model to be really true probability, but you want to know if the model is confident or not.
Yeah. Okay, so we're getting quite a few.
Also, this is supposed to be a discussion, not like a webinar. So anyone at any point you can pitch in and.
Yeah, if you want to ask your question verbally, that's cool. Or if you want to write it in the chat, that's also cool. So another question we've got is, do post hoc calibration methods change performance as well, improving F1 or AUC? So frequently, yes, they do. And sometimes they can have a negative effect on.
Should I have?
Yeah, sure. So Vahan is in the room with us, and
Hi,
he
everyone.
wants to field this question. Do you want to come sit?
That's okay, I can talk.
Yeah,
Okay.
we can't really turn the.
Yeah.
Okay.
So when it comes to model accuracy, it's important to remember that accuracy is about the argmax, right? When it's a classification problem, accuracy or advanced score are about only about the class with the maximum softmax values. So when we do calibration, depending on the method, that can change. So temperature calibration does not change the argmax, but other methods might do it. So depending on on the method of your choice, it might also change the F1 score. Not necessarily improve it, probably make it worse, but you might change the F1 score depending on the calibration method.
Mm-hmm.
Yeah, so I guess you need to assess your situation and decide based on what is more important to you. It might be that you need perfect or near perfect accuracy, and you don't care that much about calibration, or it might be the other way, or you want to like balance these two sides and get something that's somewhere in between.
Yeah. There was one thing I was going to say on that front. Okay. So another discussion topic that's come up quite a lot in the chat is talking about choosing bucket sizes. So I think it's quite a difficult problem, and it's quite problem dependent as well. So you need to, let me find what Joao said. He said it's a tough problem selecting the number of bins or the bin sizes. The more bins you have, the finer grain metric you get, but it can also end up giving you quite noisy measurements. If your bins are too small and they don't have enough examples in, then that means that the metrics you get out are subject to quite a lot of noise in aggregate. So he says to try and aim for at least 1,000 samples per bin. My experience would be to try a few different bin methods and see which ones are showing you what you want to see from either the reliability diagrams or from the metrics that we're getting out. I don't know if anyone else has any thoughts they'd like to add on that front.
I would also say that, as we mentioned in the tutorial, if you have a very, if the number of samples in different bins or different classes is very different, then best way to take that into account, and maybe especially in like the exploration part of the work, is to actually look into how many samples you have in each sample, look at them separately at first, and then assess if something like a weighted average would benefit you, or if you actually want to keep on looking at each class separately because they are so different. Depends on what you are actually doing.
Yeah, I'd agree. For instance, well, yeah, we have quite a skew in our data set, and so a lot of our data falls in one class, and so we're kind of mainly interested in how that class is calibrated. But we'd also like to print out the others so that the data from that class doesn't completely sort of overwhelm the data from the other classes. However, if you, can you guys hear me? I hope so. If you had a balanced set, then maybe you could view it all together on one plot.
Yeah, and I think there's a question, do you have a rule of thumb? I don't think we do.
Yeah.
It really depends on your data set. Like, if you have a bin with a very different number of samples for each bin, then
I think the nice thing about, for instance, what's it called? ECE. The nice thing about ECE is that you weight the differences from your perfect line by the number of examples in the bin. So if you've got a bin that's really small, then the fact that it's got a massive distance from this perfect line isn't that problematic because it's got such a low weight.
Yeah, and also kind of, again, based on what you need from your model, you can decide between EC and MC based on if you really need the maximum, like the worst case scenario to be handled correctly, or if you just care about the most of the data and you don't care about the few samples that are kind of out of your normal distribution.
Okay, so there are a few other questions. Jessica's asked about us. She's asked us to talk about nPlan, so I think we will talk about that, but maybe after we've addressed another couple of questions.
Yeah.
So I read Sina, I think, or Sina's first question about performance. The other question was, does it matter the underlying neural network is dense or RNN as long as the last layer is sigmoid?
Well, last layer is softmax.
Yeah.
But in terms of model complexity, it has been shown that more complex models, so deeper models, I'm not sure about RNNs, but I think also RNNs are less calibrated. So if your model is more complex, the general rule, the general observation is that your model is less calibrated. It's been shown in the
it's mainly the
papers.
Yeah. But when I did that small literature review section in the video, when we talked about the Guo paper, you could see a lot of the tricks that they used and the extra depth and width. It kicked up the accuracy, but also made the model less calibrated. So I don't know, you could apply this technique to, I think, any architecture. I don't see why you couldn't, but it becomes more necessary with higher complexity, I think, is what Farhan was saying. Yeah.
But the thing is, it's a post classification step, right? So
Mhm.
whatever model you have, and then after that you apply calibration.
Yeah.
It doesn't matter what models you use, right? So you check if your model is calibrated, and then if necessary, calibrate it.
Yeah, exactly. I think the big part of this tutorial is not just to do calibration on every model you have. The first part was about measuring calibration, so just measure it for your model. It might be doing great. You might not need to apply any post-training calibration method. If not, then you can try a few of these and see if they help out your situation.
I think so. And I did actually, so someone asked a question about whether calibration and training are different steps. So in what we've described here, yes, calibration and training are definitely different steps. But I think I've seen papers where people talk about certain models being more calibrated or more likely to be calibrated, or even certain training methods giving you a more calibrated model if that's what you want. So
we can try to look up these papers if we didn't list them in the resources and share them with you. So if this would apply to your case, we can, that might give you more information. There is quite an interesting question. If temperature factor is already part of your model, how should we do calibration?
Well, how is it part of the model?
yeah, that would be the question I would ask. And perhaps this sort of circles back to what Vahan was saying. As long as you are getting some kind of softmax output, even if there was a temperature factor before, you can apply temperature scaling again to that on a calibration set and come out with a scaled version of your model.
And also, I think if your concern is that that you would want to apply temperature scaling on top of your model that already considers temperature as a factor, you have other methods that we presented that you can use if this was the concern.
I suppose the only thing that comes to mind is like if you're trying to use temperature to, is it decrease entropy?
Depending which way. Right?
Yeah, if you're trying to, sorry.
Hi, can you hear me?
Yes.
Yeah.
Yeah, so my use case is that, so I have single models, and so I have multitask models, and so they all share the same, like it's a 2-tower models, and they share the embeddings, and but I have different task head, and I want to use the like temperatures to distinguish like different outputs, so that like they can distinguish the difference output can be using the same embedding, but they can have the different output. So I also want to predict or generate the temperature factors so that like for each task. So in that sense, temperatures factors is also like generated by the models and serve the following tasks. So although this is the model I learned yesterday, so I don't know the details of it, but I think if that is the case, can we find a way to do like model calibration in that use case?
So I got to say, I'm not totally sure what architecture you're describing there, but yeah, I guess I would then go back to saying if you have a softmax output or some collection of 0, 1 outputs, then you can apply this calibration technique to them to get a more calibrated probability output.
I guess this specific thing we can discuss it in the chat later on, because this sounds like a very specific use case.
Yeah.
So we might want to ask more about more details about how actually your model works and what you are trying to solve with it. So maybe if you were interested in do that.
So basically my question is, so for example, the plot scaling, they assume that the sigmoid, they don't have parameters for it. But what if our model is already modeled the scaling factors, and in that sense, can we still do the calibration?
I think you could just do another round of scaling on top of that.
Okay. Okay. I see.
Or perhaps, so I don't really understand why you have scaling in your sigmoid. Is that something you set yourself?
So it's like I have multitask, and it's a Siamese network, and because they share embeddings to distinguish different output, but I only have one dot product for two embeddings, so I need to distinguish like different task output, and that can be incorporated by using vectors, and yeah, so that's my idea.
I think you could just apply a second layer of scaling on top.
Okay, yeah, that's what I thought too. Thanks for the explanation.
No problem. Thank you for your question. So
do we have any other question, or should we go into what we do as a company?
Sana actually asked one more question.
Okay.
About observing that RNNs need more calibration than DNNs. They say they're not sure the plat method would be as effective in RNNs as in DNNs. Well, so in the tutorial, I used temperature scaling on an RNN, and it worked pretty well. And so I think plat scaling should, or as in the multi-class extension to plat scaling should. I don't see why it wouldn't work with an RNN.
But I think we have definitely had few cases where we tried scaling and it didn't work, or even sometimes made the calibration worse.
That was with the MLPs. It was simpler, right?
Yeah, I think so. I think the cases that I've seen, certainly with the right implementation, they've made an increase. They've improved calibration using those scaling methods. There are some examples, if you look in the results section of GWO, where they kind of show that they haven't been able to reach convergence because there's just too many parameters, and the space is too complicated to optimize over. So in those cases, then yeah, maybe, so like ImageNet has so many classes that I don't know if you could train enough parameters in a feasible time to get actually any better calibration. Those are the cases that I'd say maybe this wouldn't work.
Okay, does this, okay, great. Do you think there's anything else?
I don't think so. If anyone feels that they asked a question and it didn't get addressed, and maybe.
So just that you don't feel pressure to ask questions right now, we will also try to answer questions that are posted in the chat.
Yeah.
In the VFairs chat. So if you have anything that you think of later, we can try to address that or try to connect and have a chat over Zoom some other time. We are in London, so the time zone is a bit different.
Yeah. Not on San Diego time, unfortunately.
Yeah.
Okay, so one person has asked a question. Can you use model calibration for cats and dogs classification, and why? So yes, a lot of the literature about calibration is talking about binary classification models, which cats and dogs classification is. You're choosing if something is a cat or a dog. And those are, I think those are frequently the models that they can be overconfident as well, or they can not match an underlying probability distribution. And then in that case, you would just use some of the techniques that we've described in the tutorial.
So why do you need it is kind of going back to the beginning of our presentation, where we explained that if you need to know how sure of its results your model is, that's when you want to measure calibration. So you want to know if the model is saying that something's in one class just based on 60% accuracy or based on 90%, like that's a big difference for certain cases. And then also you there are cases where you want to use even a model with 2 classes for probability distribution for some reason, and then you really need to know that the outputs of your model actually represents the probability distribution, and it's not just.
Yeah, for instance, if we're talking about a medical diagnostic setting, I know we keep going back to this, but if you want to know if an image is, say, dangerous or not dangerous, cancer or not cancer, something like that, then you'd want to know how confident your model is in that choice, so you can make decisions down the line based on that probability.
Yeah, I think also it's quite valuable to just look through the chat, because some of the other people on this call have given some interesting insights from their experience.
If you join late, you can't see the chat though.
Okay.
Oh, okay.
I had that problem.
We could maybe try and save the chat before the call ends, and then post it somewhere where people can see.
Yeah, I'm gonna save the chat, and we'll try to do that.
Okay, I think let's talk about nPlan a little bit. I don't know. I'll have a go, and if I get stuff wrong, then people can jump in. So we're a London-based machine learning startup that seeks to forecast the outcomes of big construction projects. And we do that mainly through the use of a big data set we have, a data set of past construction projects that we've got through a lot of business partners that sort of, it gives us
so I guess kind of like from, I'm sorry to.
Yeah, no, please go ahead.
I think kind of more relatable way, like what does it mean to forecast outcomes of construction projects? I think everyone has witnessed the project around them where like they're building a highway or they're building a building, and it's like just taking way too long. And they have said that they are going to finish at 2019, but it's 2020 and they're still not done with it. So this is kind of the problem we are trying to solve. Not even making it faster for companies to actually build the constructions, but more for them to know how long it actually takes. You might be surprised, but even how many buildings that there have been built over the years, they really don't take the past data into account. So that's kind of what we are trying to do. Learn from the past projects they have done, learn when well, what didn't, and help them understand where the risks are and how long actually they are going to take, so that the industry can be transparent and that everyone can kind of benefit from knowing what's actually going on and not thinking it's gonna happen in a different way that's not gonna happen. But where we actually use so we have a team of software engineers, machine learning engineers, and data scientists. And we try to understand the past data, kind of like see what we can learn from it, and then also use it to predict and forecast with our model where calibration came into play.
Yeah. So I'm not sure how much I can say.
I guess in terms of calibration, I can add that calibration is particularly important for us, because Dan mentioned it earlier, because we do our predictions on each activity in a program schedule. So each project is a Gantt chart that contains multiple activities. Then we predict each individual activity, and then we use these predictions for Monte Carlo simulations. So it is important for us to get actually correct probability distributions for each activity, so that afterwards we can sample from those, and then those samples actually make sense and represent the reality.
And then we chain each of the samples. So say we take many samples and then try and understand what the project would have looked like had each activity taken as long as we sampled it to take. And that involves some sort of planning theory and yeah, basically that's how we come out with a distribution for the end date of a project. And we can then go back to whoever's planning the project and say, actually, you know, in 50% of our simulations, you're on time, so great. Or 90% of the time, you're actually going to be a year late, and we can see at which point in the schedule you've deviated from, or we predict that you're going to deviate from the plan. So yeah, I hope, Jessica, that sort of answers your question.
Yeah. Awesome. Does anyone have any questions right now, or obviously will be? Oh, so our data comes from, Jessica asked where our data comes from. Some of our data comes from the clients, so all of our data comes from the specific clients. So we have a contract with different construction companies and other businesses that do construction, and through like different contracts, we get the data from them, which is obviously secure. And then we use this data for learning. And then we have several live clients who actually have projects that are in construction right now. And we upload them to our platform and forecast on them and provide them with insights so they can learn about it.
Yeah.
We do have some conversations happening with government, but our data is so far specifically from clients.
Because the government does not make the plans, right? Government is the client of construction companies. So
yeah, certainly in this country.
Yeah, yeah. So we do have some international data, but most of our data is from UK. So that might be
also from Japan, the US.
Most of our data is UK based, and that's that might be some difference to how different companies across the world work.
So
So we work together. So we are a B2B business.
What was the question?
Does the construction company hire you, or?
I mean, we
or
can.
their clients?
Maybe we
it's
could.
a bit out of topic, right?
Yeah, maybe Jessica, if you're interested, we can catch up offline.
Fair.
And yeah,
it's becoming a pitch of empire.
Yeah, exactly. You don't want it to be too pitchy, too salesy. No
That's
problem.
okay. You can message us on like the VFairs chat directly, me or Dan.
Or there is this email.
Yeah, and we can talk about it further. So yeah, if you are interested, we are happy to talk about it. Just probably not interesting for everyone. Anyone else has questions? You can always speak up. This is not just us presenting, hopefully, even though it seems like it.
I have a question.
Yeah.
Yeah, so slightly nervous. Let's see if I can explain this. So I was just trying to understand probability calibration. So let's say that you have a model, and let's say it's a function of x, and it says if x is 3 or if x is, let's say, 7, it thinks that there's a 70% of it being true, right? And let's say that it turns out this is a so-called calibrated model. So it turns out that for those cases, it turns out it is true 70% of the time. So you'd say, oh, okay, I guess those are good probabilities, right? So I gave 2 values of x. Let's just say it was 3 or 5, right? But what if it turns out when you actually examine the model, it turns out when x is really 5, it's true 60% of the time. And when x is, if x is, let's say when x is 3, it's true 60% of the time. And when x is 5, it's true 80% of the time. And so in a certain sense, it's not actually giving correct probabilities, but in the way you guys have defined it, those probabilities would still be calibrated. And so what I was thinking is that like calibration's good, like at the very least your model should be calibrated. But in a certain sense, that doesn't necessarily mean the probabilities are correct, And in particular, you could, by looking at the model more carefully, you could actually evaluate probabilities on particular parts of the feature space and see if they're calibrated in a, I don't know, in a higher order sense. I'm just wondering if you guys have thought about that at all.
So I'm not.
Sure, fine.
Yeah, Vahan is looking keen to answer this question.
That's a very interesting point. But you could make the same argument about accuracy.
About
Right.
what?
About the accuracy of your model.
Accuracy.
Accuracy of your model.
Okay.
You can also think of it on the other end of the problem. If you reduce the number of classes, both the accuracy and the calibration will go up, usually, right? It's the same kind of thing with the inputs. If you divide the input types into more cases, you are making the problem more difficult. So I would expect to see also decrease in accuracy and calibration.
So I'm also, I don't know if this is correct, but are you kind of talking about the fact that your model might be well calibrated and then have an incorrect prediction?
Well, no, I mean, obviously it could calibrate it and yet make a lot of wrong predictions. I mean, if I think that a coin is going to be heads 50% of the time, obviously I'm still going to be wrong 50% of the time, yet my model will be perfectly calibrated. So no, right. No, I'm just talking about the case that you could have a model in which in certain cases, you're saying that I think something's going to happen with ever 80% probability. And yet it could turn out that in a certain sense, your model is actually not really calibrated. In the sense that if you look closely, you could see that really half the time it's making that prediction. Something's really happening 100% of the time, and the other half it's happening 60% of the time. And I guess my point is you could actually calibrate it on top of that. That's my point, is that in theory, you could actually analyze that. If you could look at whatever your feature space is, you could go to that next level, and then you could do another calibration on top of that. And it seems to me that in practice, especially given your business depends on that, it seems in some cases someone might want to actually do a calibration at that next level, and it would be totally a possible thing to do. And I was just wondering if you guys have thought about doing that, or if you've encountered that in the literature.
So I think João had some, it's our colleague João, ML engineer, so he might have some input for this.
Yeah, so if I understood your question correctly, you were suggesting that you might have some system which you calibrate, and then you might use that system to generate some other predictions, and you might calibrate that thing again. Is this correct?
I guess what I'm saying is, I'm trying to think about the best way to say it. I mean, I think just giving the particular example, that it might be that, let's just give, again, this very specific example. They say, I plot my calibrate, this reliability curve, and it turns out I think I'm completely calibrated, right? But then what I could do is I could more closely examine my model. I could say, it's interesting. Overall, of the times that I think it's going to be positive 70% of the time, it's actually positive 70% of the time, right? But then I could say, well, it's interesting. I'm making predictions based on this variable x. And when this variable x is 3 or when it's 5, in both of those cases, I'm predicting that it's going to happen with 70% probability. And overall, that's true. But you could say when I only look at when x is 3, it turns out it's actually happening with 60% probability. And when x is 5, it's happening with 80% probability. And once you notice that, if in the future someone comes to you and you see x is 3, you're not going to then predict 70% probability what your model says. In fact, you now have better information. And so you know that actually, in a certain sense, it's not really calibrated. And what you'd want to do, in other words, the problem is that when you plot this reliability curve, in a certain sense, you're only calibrating it in one dimension. You're looking at overall probabilities, predicted probabilities versus true probabilities, rather than doing it in a multidimensional sense, which would give you, a better sense of what's going on.
Okay, so trying to unpack your question. So I think I got it this time. What we have presented here is a calibration scheme that works for all inputs. It does not differentiate among the inputs. And what you are suggesting is that you might find that when your model is subject to a certain type of input, it might be calibrated in general, but not calibrated for this subset. So it's calibrated on average, but for this subset, it's not calibrated.
Right.
That's a good question because I haven't seen it answered in literature so far. And I think it's definitely a valid question. And yes, I think it might be worth doing another round of calibration, or designing some metric where you slice your input space in multiple dimensions, not just in bins, like as we have described in this presentation, and trying to calibrate across that dimension. And I think it definitely makes sense.
To me, it's about grouping in the feature space. That's what you're talking about.
Right.
And no, I haven't. It's not something I've seen. Definitely not. It's not to say it's not out there, but like the calibration kind of makes sense in aggregate after you've like transitioned to probability space rather than in the feature space. So I don't really know. Yeah, it's not something that I've seen. That's what I can say.
But I don't think there is anything stopping you from doing another round of calibration on top of that,
No.
as long as you don't ruin the original calibration.
I agree.
Because essentially you want some system where you take your the output of your model and perhaps the input of your model as well, and depending on the input, you adapt the output differently. So
Right.
you can create some decision tree to do that.
So you're scaling,
for instance,
for each section of the feature space. Yeah.
Correct.
I want to let other people have.
This. I haven't seen this in literature so far.
Okay. I want to let other people have the opportunity to ask a question. Otherwise, I could certainly go on about this. But thanks, I appreciate that.
If you want to have a deeper discussion, I think we would be interested. So just message either of us and we can arrange some way to discuss this further.
Yeah.
Okay. Cool. Thanks, guys.
No problem.
You're welcome. Anyone else has any questions? Or anything that you noticed that you disagree with or that you would want to add to what we presented today?
Well, if no one has anything, I want to jump into one other thing.
Okay.
On a quick related thing, do you ever have a case where, again, it's another variation on the same sort of question, where overall it's calibrated, but in a particular case where you have to make a recommendation, when you look at the particular scenario, it's kind of obvious that, you know, that really the probability is different in kind of the Bayesian sense, like you can just tell based on the features, like it's clearly an anomaly or something, and therefore you override it. In other words, do you ever try to mix what the thing's telling you with just kind of what you know to be true based on other, you know, things exactly like it?
I think if you speak about anomalies, that's like it definitely can happen, but I also think that is something that you should filter out before you even use your model. Like if you have something that's very outside of your distribution, very much outside of your normal data set and features, ideally that wouldn't come into your model at all, because it has obviously very different behavior than the rest of your the rest of your data. And you should probably approach it in a different way or like get more data about that. So that's one thing. I'm thinking if there is a way to, like, if the output is very different to the rest.
Nothing comes to mind really. I like if you have some sort of scaling that you apply to the end of your model, I can't see a case where you sort of decision tree choose to apply it / not apply it. I don't know.
Well, we have uncertainty measures. So but that's kind of unrelated. It's a bit off topic, but if the model is too uncertain, based on the other uncertainty metrics, then we would we may not give any predictions, right? We would not use the model's output. We also give the end user opportunity to override predictions, but those are rare cases, and we try to avoid them.
Yeah, so I guess it's like, obviously you need to measure multiple things about your model. Calibrations should never be the only way you decide what to do. And for example, in our case, if our model is very uncertain, we can decide to tell to the client that we can't really provide any predictions for their data because it's so different from whatever we have seen, and we are not confident enough to tell them anything. Yeah. Or then there is a few methods that you can test out that are not machine learning methods, like to kind of provide some level of input, but not on the same level.
Using only prior information.
Yeah.
For example. Yes. There are a few things we can do for special cases, yes, but they are not necessarily about calibration.
Mm.
Yeah.
Hopefully that helps a bit, Jason.
Cool. Thank you.
I think we're happy to continue this conversation either in the group chat or privately because it's certainly interesting. So, yeah, and we are not trying to say that we know everything perfectly. So we are happy to learn from. There have been a few articles shared in this chat that have been quite interesting, and we are happy to read them and see. I'm going to save the chat and try to share later what I think is some information that's interesting. So I think if there are no other questions right now.
Oh yeah, we could.
Yeah, so we are going to end this session now. If you wanna rewatch the video or you didn't get the chance to actually take part, it's shared in KDD, and I'm pretty sure we will share it as a company later on.
Mm-hmm.
Other than that, as a company, we have lots of ML engineers who are very smart and data scientists who are very smart. And what we try to do is share this knowledge and exploration with other people in the industry or people who are just interested. So what we do is our weekly machine learning paper club, where we read a interesting paper every week. Someone will present it, sometimes from our company, sometimes from elsewhere, and then just share the link to the paper club in the chat. Since lockdown, we have decided to move it to more virtual sessions, so anyone can join, which is great because we are not limited by the size of the room.
And also anyone can present as well. It's a place to discuss papers, not just to listen to papers. So we've had a few people from outside the company come and talk about different things, and yeah, it's a great place to come and talk about machine learning resources and new papers that you found that you think are interesting.
Yeah, and lots of interesting discussions are sparked in this space. So I would definitely encourage you to look at it, and if you see a paper that you are interested in, you can join.
Cool.
Is there anything else that we missed?
I don't think so. Yeah, I guess I don't know if we're going to try and upload this to the VFairs thing, but if someone's watching this back, then please send us a message in the chat, or send us an email in the email that I posted in the chat, and we'll try and field those questions.
Yeah. I think that's about it.
Cool.
Cool. It was very nice meeting you all, and thanks for
sticking with us. Hope you found it useful, and yeah, enjoy the rest of virtual KDD 2020.
Bye.